Okay, so conservation of energy is something that we've done a lot, and it's been embedded within some of the problems that we've done throughout this unit, but now we're just going to take some notes on it and really tie up any loose ends that we may have and really start applying them to real world situations. So the work-energy relationship, this is something that I've previously shared when we first introduced gravitational potential energy. And it says that the work done in lifting an object to a new height is equal to the object's increase in gravitational potential energy. So if I have some table here, and let's say I have object A here, and I want to lift it to the height, whether I lift it in that path, if I lift it in a path something like that, or if I go all the way around here, regardless, the amount of work done is going to be the same because that path is the same. Where this would not be the case is when we have something that's considered a non-conservative force. So in this case, the force of gravity is a conservative force. Now, if we have a non-conservative force, so let's say I have the same table, but now all of a sudden I have these inclines. So we'll call this incline A and incline B, and both of these are rough inclines, with B being a little steeper. If I place that same object A at these two locations, well, it's going to take longer. It's a longer distance when you're pulling it up A. You also have to pull it up at a different force because we're talking, take into account the components. Just so knowing that a non-conservative force will impact that, because once we get into the conservation of energy, some of that energy will be converted to heat as well. So for now, when we focus on conservative forces such as gravity, that work done is equal to the increase in potential energy. So the law of conservation of energy says energy cannot be created nor destroyed within a closed system. And what a closed system is that no outside forces act. And we've looked at that, when we've talked about dynamics and Newton's second law. Also, something that we have introduced a little bit in class is mechanical energy, which is the sum of potential and kinetic energy. So we got PE plus KE equals mechanical energy. And this is really helpful to solve these conservation of energy problems. And an ideal mechanical system is a system where it's closed and there's no friction or other non-conservative forces acting. Other non-conservative forces may be things like air resistance. So that is not the case for an ideal. Okay, so building off of that, a good example of an ideal mechanical system is the pendulum. We looked a little bit today when we had that oscillating spring, and oscillating was a new word for us. So a pendulum, if you've ever seen a grandfather clock or anything, or a simple pendulum, it's going to swing back and forth, right? And that just means that it's oscillating. Oscillating means it's following regular cycles at repeated time intervals. So for this case, if we consider the pendulum swinging back and forth, well, in this position, it's changing direction. And so when it reaches the end, it's changing direction. When something's changing direction, I'm going to put little extenders here. When something's changing position, its velocity is zero because it's changing direction. So at the top position, it's going to be all potential energy, and the kinetic energy is going to be equal to zero because it has no velocity. At the midpoint, where it loses half of its height, so over here I can't really fit it in, but if this were h, then this would be 2h. Okay, so at the exact half point, the potential is going to be equal to the kinetic energy. And then at the bottom, well, this pendulum, it can't go any lower than that, so it can't lose any more height. So at the very bottom of these systems, the potential energy is going to be 0, and this is going to be all kinetic energy at this point. So what this means is, however much potential energy we lose, all of that potential energy we lose is converted into that kinetic energy. Okay, and conservation of energy, it's also helpful when we're looking at things that are falling some height. So we've used the free fall formula in the past. Let's say we have some cliff and we're dropping an object from rest. So at the very top, it's dropped from rest, it's going to be all PE. And then when this falls and hits the ground, all of that potential energy is converted to kinetic energy. So the potential at the top is equal to the kinetic at the bottom. And we can plug in, we have gravitational potential energy, we have mgh equals 1/2 mv squared. And on both sides we have mass, so I can cancel out the masses, and we're going to left with gh equals 1/2 v squared. And we could rearrange this. If we had the velocity, we could solve for the height. If this case, let's say we had the height, we could solve for the velocity that this object will hit the ground with. So I'll move over the 1/2, I get 2gh equals v squared. Gotta get rid of that squared. So this velocity would be equal to the square root of 2gh. And that formula would work for anything that is falling. For non-ideal mechanical systems, that's like the first page where I had the different inclines and where friction's acting. So energy is still conserved in these situations, but in a non-ideal system, the energy total is going to be equal to the potential energy plus kinetic energy plus Q, where Q is heat energy, or something called, it's often referred to as internal energy. Okay, and they all have units of joules. So if we take this a step further, I'm not going to attempt to draw a skateboarder, but let's say we have a half pipe, right? This skateboard ramp. So if this were a frictionless system, this skateboarder would go up and down, right? And they would always get to that maximum height. Now, if there were friction here, this skateboarder, and they were dropped from rest, they would not reach that maximum height. But where they reach the top of their flight, I'll call it, or when they reach the top of the height on that particular path, they're changing directions. So let's say the potential energy here is 100 joules. Now, at this point, the kinetic energy is 0 because the skateboarder is changing directions. So in this case, if the potential energy, I'll use a different color. If the potential energy is equal to 75 joules, well, we know the kinetic energy is 0, but this object, this system still has to have a total energy of 100 joules. So 25 joules would be converted into internal energy. And again, we'd use that to figure out, we can manipulate this formula to figure out either of these values.